Okay, today we are looking at tables to decide whether our rates of change are linear, our rates of change are quadratic, or are they something else? Okay, so of course you think of the average rate of change as the slope of your line. Okay, slope is a comparison of two values. It's the change of your y value compared to the change in your x value, right? So you can have little steps on here, your change in y over change in x, right? So there's your delta y. The vertical part is your change in your y values, and the horizontal change is your delta x, your delta y over delta x, change of y over change of x. Okay, and we of course call that the average rate of change over your values. Okay, so we're going to look at our x and y's here and decide what is our average rate of change. Okay, so looking at the x's, if we started at 1 and we're now at 2, how much did those change? Those changed by 1. We were at 2 and now we're at 4, those changed by 2. We were at 4 and now we're at 8, those changed by 4. Okay, so these are the changes in your x values. This is your delta x, your denominator of your rates of change. And now let's look over here at your delta y, or your changes in the y values. We were at 4, now we're at 7. That's a positive 3. We were at 7, now we're at 10. We were at 10, now we're at 13. 3. So all of those are your change in y. So what can we say about our average rate of change? Is it linear? Is it quadratic? Or is it neither? Okay, so let's look at our change. So the change is your delta y over delta x. So this first points have a slope of 3 over 1, which is positive 3. Okay, so from an x value of 1 to 2, our y values have a change of 3. Now let's see if that is the same as we go down. What is our average rate of change from our next 2 points? Y value of 3 and an x value of 2. Okay, are these two rates of change the same? Right? No, they are not the same. They're not constants, which tells us that this is probably not going to be a linear equation because our rates of change are different. Now our last one, if we look at the delta y, we have a 3, and at delta x we have a 4. So now we have an average rate of change of 3/4, which is different than both of these. So of course this one is not going to be linear. Explain why f of x is not linear. Our rates of change are not constants. Okay, we have a change in our rates of change. C-O-N-S-T, constant. In order for us to have a linear function, the rate of change must be the same no matter what interval we're talking about. So this next part says, think about the quadratic function x squared, right? That's our parent function, y equals x squared. And let's first of all figure out what our y values are. Okay, so if I have an x of negative 3, what's negative 3 squared? Good, positive 9. And then negative 1 squared is positive 1. And then positive 1 squared is positive 1. And the positive 3 squared is 9. And positive 5 squared is 25, right? So all of our g values are found by squaring your x value, right? That's our parent quadratic function. So now it says, complete the table and see about our average rates of change over these certain intervals. So we're going to look at this constant interval of 2 from negative 3 to 1, and then the interval from negative 1 to 1. So all of these have an interval change of positive 2. Right? So all of our delta x's, if we look at the average rate of change as the change in y over the change in x, for every one of these, they're all going to have a denominator of 2 because our x values are all changing at a rate of 2 every one of our table values. Okay, that just so happens to come from this. It won't always be 2, but that's the way it is right now. So if we look at from -3 to -1, remember that's y2 minus y1. So let's see, y2 would be, this is your x2 and this is your x1. So y2 would be positive 1 minus an y1 of 9. So 1 minus 9 divided by 2 is going to be -4. Right? So 1 minus 9 is -8. -8 divided by 2 is -4. Okay, let's look at our next interval from -1 to 1. We had a y value of 1 as your y2, and 1 minus 1. What is 1 minus 1? 0. So from -1 to +1, our average rate of change was 0. Okay, what about from 1 to 3? That would be 9 minus 1. So 9 minus 1 over 2 is 8 divided by 2, which is +4. And then we have 25 minus 9 over 2. 16 divided by 2 is 8. Okay, so look at our average rates of change. How are they changing? We went from -4 to 0, so that's a change of +4. We went from 0 to 4, that's a change of +4. We went from 4 to 8. So notice our average rates of change have a constant rate of change. Okay, so our average rates of change have a constant rate of change. It's the rate of change of your rate of change, right? It's kind of interesting to think about that we can do that. If this is the case, if your rates of change are constant, then we're looking at a quadratic type of a function. Okay, our average rates of change. Okay, so that's what we notice. What do we notice about the average rates of change? Well, they are constants. Your average rate of change is, of the average rates of change, is constant. Okay, so it's how our slopes are changing. So let's move on and see if we can figure out whether it's a linear one or whether it's a quadratic one or whether it's neither, based upon the slopes of your rates of change, right? The rates of change of your slopes. So let's do this. How is the x's changing, right? We have our delta x on this side. From 1 to 2, it's gone up by 1. From 2 to 4, it's gone up by 2. From 4 to 7, it's gone up by 3, right? So those are your delta x's, which is fine, right? Nothing wrong with that. They're increasing at a non-constant rate. But then our y value from 0 to 1 is, and from 1 to 4 is 3, and from 4 to 9 is 5. Okay? So if we look at the rates of change, right, we are looking at 1 divided by 1. What's 1 divided by 1? It's 1. 3/2 is the next one. That's our next rate. So we know that it's not linear based upon that information. Right? We have a 1 slope, and then we have a 3/2 slope, and then we have a 5/3 slope. So we know that it's not a linear function. But what if we evaluate your delta y's? How are these changing? What's 1 to 3 is a +2. 3 to 5 is a +2, right? So this is the rate of change of your slope, right? The rate of change of your delta y. Is this one a constant? Because if the second rate of change, right, if your y values are changing at a constant rate, then you have yourself a quadratic type of a graph. Okay, so 1 to 3 to 5 to 7 are the increasing in your y values. But if you check those ones out, then you see that you have a constant rate of 2. So we have ourselves a quadratic type of a linear graph there. Okay, let's look at this. 1 to 2 is a 1 change, delta x. and then we have a 3, and then we have a 5. Delta y, so we're looking at these ones also. 0 to 1 is 1. 1 to 4 is 3. 4 to 9 is 5. So if you're checking out your delta y over delta x, 1 divided by 1 is 1. 3 divided by 3 is 1. 5 divided by 5 is 1. All of these slopes are the same, which means this is going to be a linear function, right? Your rates of change are the same. Your delta y over delta x is the same. When we compare the change in y to its corresponding change in x, all of these come out to be the same. But they weren't over here, right? We had a 1 and then a 3/2 and then a 5/3. So our initial rate of change, your delta y over delta x, was not constant, which is why we looked and saw if we had another one. Here, your delta y over delta x is all the same. They all reduce to the same 1, so we have a linear equation. Okay, and then our last one here, this last example, this is a 1 and a 1 and a 1. Okay, those are all your change in x's. We have intervals of 1. And this one is 1 and then 3 and then 5. So we look at the second, and we get a 2 and a 2, right? So now we have a delta y that's not constant, but we have the rate of change of delta y, which is constant. So this is what gives us your quadratic. Okay? And the delta x is still 1, right? So these are all the same. The delta x is constant between there. And your rate of change of your y values is the same. So you have a quadratic when that happens. Okay, so there's some of those on your assignment today also. Okay, and then what about concavity? Can we tell from a table whether our graph is concave up or our graph is concave down? So let's see. Let's look at our let's plot it. I like to see this. Let's plot this on an XY axis real quick and see what it looks like. So these are decimals, so I'm going to put 1 here and 2 there, and then these are going to be, bless you, very decimal. So I have 1 is 4, we'll put 1, 4 right here. And then 1.1 is at positive 1, so there's 3, 2, 1. 1.1 is really close in there, so there we have like that. And then 1.2, we're at negative 1, which is down here like that. 1.3, we're at negative 2, which is a little bit closer in like that. So what might we say about these points here? What kind of concavity do you think this graph could have? Concave up? You think it's concave up? Right? It might be, but let's look at the rates of change. So we have 0.1 and 0.1 and 0.1. Okay, right? That's all of our x values are changing at 0.1. And now let's look at our change in y. From 4 to 1 is negative 3, right? It's gone down 3. And then from 1 to minus 1 is down 2. And then from minus 1 to minus 2 is down 1. So if we do our rates of change, negative 3 over 0.1 is negative 30. Right? That's the slope of that line, negative 30. Negative 3 divided by 0.1. And then we'll do negative 2 divided by 0.1, which is negative 20. And then we'll do negative 1 divided by 0.1, which is negative 10. Okay, so what can we say about the rates of change? The rates of change are decreasing. Oh, actually, the rates of change are increasing. So sorry. The rates of change are increasing. Now, why are they increasing? because it's getting more and more positive, right? It's getting more and more positive. Negative 20 is closer to 0 than negative 30 is. And anytime we're on a number line going from left to right, our values are increasing. Okay? Yes, they're still negative, but they're negatives closer to 0, so we say that is increasing. So this one is going to be concave up. Whenever your rates of change are increasing, your graph is going to be concave up. So we can put that up here. Whenever your rates of change of equal length are increasing, you're going to have a concave up graph. Which means on the flip side, what happens if they're decreasing? It's going to be concave down. Right? Getting more negative. Decreasing means they're getting more towards the negative part of our number line. So once again, we have a delta x of 0.1, right? So constant 0.1, 0.1, 0.1. Here we have plus 3, and then plus 3, and then plus 3. So our rate of change, 3 divided by 0.1 is 30. Okay? So is our rate of change increasing or decreasing? It's staying constant, right? So if we have a constant rate of change, then it would be neither concave up or concave down. Okay? In order for our graph to be concave up, our rates of change have to be increasing. And in order for our graph to be concave down, our rates of change have to be decreasing. Right? Here they're staying constant. 30 and 30 and 30 means that we do not have concavity of our table. All right, last example. Still have a delta x of 0.1, right? Constant change in x. Here we have a change of plus 6, and then we have a change of plus 4, and then we have a change of plus 2, which means we have a rate of change of 60, and then 40, and then 20. So what can we say about our rates of change? These are decreasing, right? They're getting closer to 0, which means our rates of change are decreasing. So our graph is going to be concave down. Concave down because our rates of change are decreasing. Okay? So whenever we're talking about concavity, we're looking at the rates of change. And when we're talking about quadratics versus linears, are those changes constant or are the rates of change not constant?